Okay, good afternoon, bon après-midi. Welcome everyone to this edition of the McGill Physical Society Colloquium. I'm coming to you live today from the brutalist majesty of the Rutherford Physics Building, where the walls are gray, but the bandwidth is high. Just a reminder that everyone is being recorded and live streamed to YouTube. If you do not wish to be recorded or live streamed in the Zoom session, please log off and join us via YouTube. And I'll give you a quick explanation of the schedule just before I introduce the speaker today. So there will be a 45-minute talk followed by a 15-minute question and answer period. After the question and answer period at about 4:30 p.m. Eastern time, there will be an après-colloque. For the après-colloque, the faculty members in the audience will be asked to log off of Zoom, and anyone in the Zoom session will have the opportunity to meet the speaker in person. The après-colloque is not recorded and it's not live streamed, so the live stream recording will end at that time. For the question and answer period, I'll just remind everyone that if you want to ask a question at the end of the talk, if you're in Zoom, please raise the hand feature. Your name will pop up to the top and I or my collaborator will pick you and call on you one at a time to ask you to ask your questions, unmute and ask your question. If you want to ask a question on YouTube, please type something in the chat. Just a quick reminder that you do have the power to unmute yourself in this session. Please do not abuse this power. If you do abuse it, you will be removed from the session. So that's it. So I would now pass to the introduction of the speaker. Today, I'm very happy to introduce to you Dr. Marissa Giustina from Google Research. I encountered Dr. Giustina's work for the first time when I saw a paper that was published in Nature on closing some loopholes in the Bell inequality tests. Dr. Giustina was doing work that is extremely important and integral to quantum information research, and it was in direct competition with some friends of mine who were working at NIST in Colorado. Dr. Giustina started out as a mathematician. She completed a BS in mathematics at Mary Baldwin University, after which she went on to do studies in electrical and materials engineering at Dartmouth. She studied under the famous group of Anton Zeilinger at the University of Vienna for a PhD, which she completed in 2016. And since that time, she's been a quantum electronics engineer at the Google Quantum AI Lab. So she has done work on what I would consider 2 of the 5 most important papers published in quantum information in the last 5 years, 6 years maybe. So it's quite a good start. So the young scientists in the audience, please take note. This is how it's done. And this is not her first time at McGill. I learned that she came previously for a woodsman's competition. She had a much more tactile experience, I imagine, on the Mac campus in the West Island. So we're very happy to have her back. And this time she's going to tell us about some fantastic science that she's been doing in the Quantum AI Lab. So with that, Marissa, please, Dr. Giustina, please take it away.
Thank you. Thank you for that very fun and very flattering introduction. I hope I can live up to some of that with the presentation that I'm going to share with you today. This is going to cover work that's come out of the Google AI Quantum team over the last couple of years at this point. So this is not solely my work, but it is work that I have contributed significantly to in a strong collaboration with a pretty big team. And one thing that's sort of certainly worth highlighting is you mentioned the work that I had done in the past. There's been, for me personally, a pretty big set of experiences from working on a project where I'm working more or less by myself to understanding how to integrate into what has grown into a pretty large team. And those are both very different but very rewarding experiences. At some point, I think to build something this large, you do need a big team. So I'll talk a little bit actually about how that team got started and then get into some of the work that we have been doing as a team. I kind of went back to 2012 when Hartmut Neven, who is a computer scientist and actually was a computer vision expert, was working on some optimization problems, as there are many optimization problems in teaching computers to see. And he kept stumbling across quantum information, quantum computing, and he was a Google employee and wanted to know, okay, what is this quantum computing stuff? How is it relevant? How is it relevant to my work? How is it relevant to Google more broadly? How is it relevant to the world as a whole? And got some people at Google to give him some permission and money to devote resources to learning about quantum computers. He actually leased a E-Wave machine in collaboration with folks at NASA, started to learn a little bit about quantum computing. And then a couple years later in 2014, this is somehow typical of the way Google tends to do things, I'm observing, they said, oh, okay, actually now we want to build one ourselves. So that's great, except he had no idea how to build a quantum computer. It's he's not alone, right? It's a hard problem. And so to do this, they engaged the group of John Martinez at UC Santa Barbara, who had much experience in superconducting qubits already, and unique in some ways in this field, really a hybrid mindset of both strong physics research, but also a fondness for engineering and an appreciation and a tendency to seek out good engineering. And so I had hoped specifically to invite not only physicists, but also engineers to this talk today, because it's really, this work in particular is born out of a strong marriage between good physics and good engineering. So in any case, that motivated, I think, the Google people to bring in specifically this effort. And now if we fast forward to today, we actually are about a 70-person team, a little more than that at this point, and spread out mostly along the West Coast of the United States. There are people elsewhere as well, but primarily we have the applications, algorithms, physics, theory work done in LA, actually in Venice, California, which is where Hardmut was located and where his group was located. Then we have the hardware research in Santa Barbara, and it has stayed in Santa Barbara. And then actually up in Seattle, we have a small army of software people, and they are the interface that helps us down in Southern California talk to each other. So we have hardware that we're building in Santa Barbara and that we're setting up in Santa Barbara. We would like our first users, our first external users, to be our own theory team. They're 1.5 to 6 hours up the road, depending on traffic in LA. And to help us communicate with each other, we got help from these people, from the software engineers up in Seattle. So we've been doing this remote team thing for a while. That said, the impact of COVID has still not made it easier. So moving from there, suppose you have this team and now you want to build a useful quantum computer. Where should you start? Well, we should start by figuring out what that means. So what is a useful quantum computer? We'll start with the noun and work backwards through the adjectives. Computer, of course, that is something that is a machine that can perform computational tasks. Then, okay, it should be quantum. That means we need a controllable system with many quantum bits, qubits, and that translates into harnessing zillions of probability amplitudes in physics land. So that's kind of the device itself, but of course we also want it to be useful. And that means that it has to be good for something. It has to be usable for something, and we have in mind a universal error-corrected quantum computer. And so what's meant by that? Well, quantum information as stored physically is fundamentally error-prone. There are errors given to us by nature that we can't get away from. So without research in quantum error correction theory, it's actually unlikely that we would be confident about doing the hardware research at all. And thinking back a good 25 years, in 1995, Peter Shor sort of proposed for the first time a system of how error correction could work with an assumption that we can describe a quantum computer using a digital error model. And that basically means that all errors in the evolving quantum state can be characterized by a set of localized bit flips and or phase flips. In other words, that means that we could track a full system level errors simply by knowing only what the discrete errors are. And this is actually kind of a radical suggestion. It's not obvious that this should hold because a quantum system is decidedly not just the sum of its parts. The integral to the concept of a quantum system is the ideas of large-scale entanglement. So thinking that we can track knowledge of a full quantum system simply by discretely knowing the errors is not necessarily obvious, and it is something that definitely needs to be tested. Can the errors in a large quantum system be treated as discrete and probabilistic? And that's something that I'll come back to several times in the rest of this talk. Of course, another part of good for something is that somebody has to be willing to and interested to use this thing. So we definitely need to develop a good handshake between the hardware developers and the algorithm developers. So, okay, that's our goal. Where do we start? Well, we better start by building a prototype. And what do we want in that prototype? Well, it's basically the same list. We'll go through it forward this time. We want something that's error correction compatible. We want to be interfacing with algorithm developers. We want system-wide control of our quantum system, and we would like to demonstrate that this computer could do something, and this prototype could do something. So for error correction compatibility, well, we are thinking in the long term for this universal fault-tolerant quantum computer. We are a superconducting qubit lab. We are interested in a surface code setup because it has a reasonably favorable error threshold, and it is convenient for building out of superconducting qubits in a 2D array with nearest neighbor coupling. So in this box, you see some black circles and some white circles. Those are the so-called data and measure qubits, respectively. We can perform parity measurements between them to track errors and basically encode a single physical qubit, a single logical qubit out of a large array of physical qubits. So this whole block here can be used to encode one qubit of lower error than the individual constituent qubits that construct it. That system will take something like 1 million qubits or so in order to become really fully universally fault tolerant. And up until about a year ago, the state of the art in publications was on the order of 10 qubits, actually 9. There are 9 in this picture. And so our prototype, we can't certainly start our prototype of with 1 million physical qubits. So let's look for some intermediate milestones of where we might place this prototype or target this prototype. Already at around the 1,000 qubit machine, we can start testing the error correction protocol that I've outlined over here. We expect that with the error rates we have right now, or that we expect we can achieve right now, something like 1,000 physical qubits can make up one logical qubit, roughly. So at around 1,000 physical qubits, we can already start seeing this error correction work converge. But the jump between 10 and 1,000 is also pretty big. So let's consider again where we might want to place our prototype. And we look as we look at this line of qubit number and capability, something we observe is that already at around 50 qubits, it is no longer possible for any classical computer to replicate, to fully simulate what that system of 50 qubits can do. And this is work in progress in the classical computing community. There's changes, and there's certain there has actually been significant development in the last 4 or 5 years, but the limit is around 50 qubits. And each time you add an additional qubit, it becomes twice as difficult. So that becomes a pretty hard line at some point. And beyond that line, we enter what we call the noisy intermediate scale quantum regime, where we're entering a regime no classical computer could reach. There may be something interesting there. And so that seems like an interesting place to plop our prototype. We get to a point where we can't explore, we can access a space that we could not explore with any other computing tool that we have today. So back to our prototype list, what should we build? Let's try to build something of around 50 qubits. Let's put them in a 2-dimensional array to make it surface code compatible, error correction compatible into the future. And of course, we also want to interface with algorithm developers. Now, in this NISQ era, this noisy intermediate scale quantum era, we know that the algorithms we can build are going to be very hardware specific. It is not the case that everything can get compiled away into some generic quantum hardware agnostic system. And so in this era in particular, we need to establish a strong collaboration between hardware developers and algorithm developers. To this end, we have developed an open source Python framework specifically for developing algorithms in this regime. It's called Circ. If you Google Circ and look it up, you can find information about it. You can download it. You can start playing with it. It features some nice ASCII art. It's pretty simple to use. And moreover, it forces an algorithm developer to be quite aware of the specific layout of qubits they're designing for, so that you don't design an algorithm and then discover, oh, but there's no hardware that can actually run this thing. I've tried to couple qubits directly that are on opposite sides of the chip and can't actually talk to each other. So that is built right into this platform. Moving on, now we need to actually build such a system. So we need to demonstrate adequate control over the system. That means adequately good gates and readout for this whole array. To take a quick step back, or to step back to foundations, I'll try to capture in one slide the essence of a long study that occupied my time in my own transition from foundational studies of quantum mechanics using optical photons to foundational studies of quantum mechanics using microwave photons. And so what is a superconducting microwave qubit? Well, let's start with this perhaps more familiar friend, the LC harmonic oscillator. This guy has a parabolic potential, a parabolic energy potential with evenly spaced levels separated by a frequency, a resonant frequency, we'll call it omega r. And this is decidedly not a qubit because you have no way of controlling which level you're in. If you excite by omega r, you inject energy of omega r, you can transition up and down this ladder and land anywhere. And in a qubit, we would like to have ideally a perfect two-level system where we can be certain that we're either in the 0 state or the 1 state. So to access that, we can add a nonlinearity. We can replace that inductor with a squid, or a Josephson junction. It is a nonlinear inductive element whose inductance depends on the amount of current flowing through the element. And that pulls this parabolic potential into a cosine potential. And it also allows, or thereby allowing, the frequency spacing between the different levels to be different. So we introduce this anharmonicity, and now the 0-1 transition happens at a different frequency than any other transition, and we can effectively isolate that transition to operate our qubit. So in short, the quantum information, the word qubit is overloaded. It's the fundamental unit of quantum information in an abstract level, but now we're making it physical as well. So that quantum information, that qubit, it's represented in the amount of energy stored in this little circuit. Okay, so how do we build that thing? Well, fortunately, we can leverage lots of clean room and silicon processing expertise that's been developed in the semiconductor industry over the last decades. We use a clean room facility or a foundry, and we make these actually fairly simple circuits out of aluminum patterned on silicon. So we basically have these three elements, or two elements even. We have our capacitor and we have our squid made of two junctions. The capacitor is that yellow plus sign in the middle. There's capacitance to the ground plane on the outside. And then at the bottom, you can see we have these two Josephson junctions, which are little overlaps of aluminum fingers with a small insulating gap in between the two. So we also, coming back to elements that you may see on a chip, we have these resonators, these superconducting resonators. This is the more familiar LC oscillator. We actually make our resonators out of waveguide transmission line pieces. So when you look at micrographs of these chips and you see these little snakes on there, what are those? Those are resonators. And if you think back to perhaps an early physics class where there was a string bolted to the wall on one side and you can wave it on the other and you can excite some modes in that string, it's the same concept here. We have a voltage node on this one side where we're shorted to ground. We have an antinode on the other side, and the length dictates the resonance frequency of this resonator. So when you put all of this together, you may get a chip that looks like this. This is a picture similar to that 9-qubit device I showed on an earlier slide. And in fact, we have our qubits, which are these plus-shaped guys in false color. We also use resonators as part of our readout scheme, and we have some control wiring. Now, our goal in the prototype was to make a 2-dimensional thing, and you can see very quickly that we're running out of space. There's an obvious problem. There's no place to put a 2-dimensional array. We've already filled up 2 dimensions. So the thing that we needed to do, or a piece of technology development we needed, was to actually separate the control wiring and the measurement stuff, put that someplace else so that we can pattern qubits in a 2-dimensional array. And the way we chose to expand was to just bring in a separate chip. We have a substrate chip that contains control wiring and these additional readout resonators. And then we have the qubits on a separate chip, and we can connect between the two with an array of superconducting bump bonds. And this technology is very commonly used in industry packaging at this point. It doesn't normally have to be superconducting because most conventional electronics are not superconducting, but indium is a superconductor and is a common, nice, squishy material to use for this. So we've brought up this indium bump bond process to allow us to connect the wiring and control on the substrate with the qubits themselves on the chip. And at that point, building a 2-dimensional array just becomes as simple as coming up with a good unit cell and then stamping that unit cell a bunch of times. So we put a lot of design work into coming up with one unit cell where we can multiplex, at this point, 6 qubits onto a readout line. We can compact all of the control and readout stuff that we need in the space of around each qubit or between each qubit, and then we can just stamp that thing. And whether we need 54 qubits, as we have in this particular array, or some other number, it's just a matter of copy pasting another few of those unit cells. So at that point, we could build this device. And here's an image in the top left of the hybridized device itself, where we have the carrier wiring on the bottom and the qubits are face down on top. That thing goes into a package that allows us to access the wires themselves with cables. So you can plug a cable into the package, and then it's wire bonded to the chip to route the signal from the cable to the chip itself. That package then gets mounted in the base of a dilution refrigerator, and we cool it down, and then the real work starts. And I say that a little bit jokingly. A lot of the work that I have done in this project is actually visible on this slide right now. And there was quite a lot of work, but we should by no means think that that's the end of it. In some ways, that is just the beginning. The next thing we need to do is calibration. And I picked up this analogy from a colleague of mine who works on the calibration team, and he's a musician. He pointed out that the process of calibrating a quantum computer has something akin to learning to play music. Just as a musical instrument generates a sound, and the listener interprets that sound as a note, and what makes a good musician is having a very well-calibrated musician. They know exactly how to produce the sound wave they want in order to get the listener to hear the desired note. Well, similarly, our control electronics are like instruments, and we play electronic waves as music to our qubits. The qubits will respond to the electrical waves that we send according to the shape, the frequency, the waveform that is sent down. And we want to make sure that we want to basically teach our control electronics to make the right electrical waves to realize the quantum gate we want. So if we want to, say, rotate the qubit around the Bloch sphere, then we need a very particular electrical wave, and we need to figure out at the electronics level what specific wave packet to send in order to realize that gate. It's a nice addition to the analogy that our notation for quantum gates kind of looks like music notes. So I have these little white boxes are the single qubit gates, and these little blue tied boxes are gates that couple 2 qubits together. Now, if you have 50-some qubits and you need to calibrate them all, that is a lot of work. If you have just 1 or 2 qubits, you can imagine going in with your arbitrary waveform generator and your oscilloscope, and you can fiddle around for a while, and eventually you can tune up the parameters so that the gates do what you want. If you have 54 of these to do, you cannot do it all by hand. So one of the really important pieces of development in the calibration work we did was to automate things and to learn how to how to write software that could do the calibration for us. That also means that we cannot rely on any hero effort. It cannot be that, oh, this isn't quite good enough. I'm just going to put in a little more elbow grease and I will be able to do it better because I just pushed extra hard on this one qubit. No, we need to write good enough software that can operate correctly across all the qubits and deliver a good product. And so what we have done is separate the steps of calibrating qubits into basically this graph. And this is our set of steps needed to calibrate, or this represents the set of steps needed to calibrate a single qubit gate. Then we will check and see how the gate is performing and continue improving on this until we get a graph, until we get a performance that is as good as we need. So how do we check the performance? Well, at a quite simple level, we have this method called cross-entropy benchmarking fidelity. And I don't want to get into too much detail on what exactly that is, but consider it as an accuracy score that allows us to tell whether the gate is doing what it's supposed to do. So at a simple level, we could start at an zero initialized qubit, perform a gate, measure what the state of the qubit is after that. We will get an output that is either 0 or 1. And we can repeat that many, many times and see if the output statistic is what we would expect for the gate that we tried to employ. Then we can add an additional gate and more gates, more and more gates.
I'm sorry to interrupt. Are you advancing your slides? We still see the music analogy.
Oh dear, I'm sorry.
It may have stopped for some people.
Thank you. Can you see it now?
Yes, now it works. Thank you.
Okay, sorry. So, thank you very much for pointing that out. I was highlighted the wrong thing. So this is the picture that I described before of the graph for calibrating single qubit gates. There are a lot of dots. Each of these dots represents a step in the calibration process. And so you can still see this? Good, okay. So if we wanted to check the performance of our gates, as I was mentioning before, we can use this accuracy score. We can run one gate, measure the output, it will be either 0 or 1, and we can check to see whether that is what we would have expected for the gate we were trying to run. And we can add more gates and more. And as we add additional gates, we expect that the accuracy score will drop, but we should still be able to get an understanding of how well our gates are performing. And we can use this approach also to calibrate the performance of, and estimate the performance of 2 qubit gates. So these blue gates are 2 qubit gates, and these white boxes are for single qubit gates. Now, let's go back to this. Of course, we need to calibrate also 2 qubit gates. And so the procedure for automatically calibrating 2 qubit gates is even more complicated than for a single qubit gate. And of course, as I said before, all of this needs to be automated because each of these nodes is essentially one physics experiment, one calibration step that we need in order to reach that final ideal waveform. And for 50 plus qubits, there are thousands of these. And some of them are reasonably simple, but many of them are actually quite complicated. My colleague, the musician who came up with the music note analogy, his PhD was just the contents of that little circle. So this is not just a day's work. This is really quite a bit of effort. And if we don't automate it, we have no chance of succeeding to calibrate a large chip. But we did, in fact, automate it, and we managed to calibrate the full chip, the full set of, in this case, 53 qubits, to an error level that we're pretty proud of, in particular because these are not errors measured in isolation. This is the performance of the entire chip operating together as a system. So each qubit, for most qubits, typical qubit is connected to 4 nearest neighbors, and these single and 2 qubit error rates are when the system is operating in a state of every qubit being connected to its neighbors. The errors, so you can see in this graph, there are plus shapes and there are squares. The plus shapes correspond to single qubit errors. The color of the plus shape corresponds to the single qubit error, and the color of the box corresponds to the 2 qubit gate error for that particular qubit and set of qubits. And then we have readout error in addition. So this was sort of our performance that we achieved, and with that we said, great, we've built this whole big system from control electronics to cabling to the chip, and then we have calibrated it as well. We've demonstrated a good system-wide control with good gates and readout. With that, we would like to give it a test. So we would like to check that it can perform some small milestone computational task. And with that, well, when we chose this prototype size in the first place, we decided it would be interesting to pick this 50-some qubit level, because that starts to push into the NISQ regime where we hope we could beat a classical computer at something. We hope we could develop hardware that can plow into an area that we cannot explore with a classical computer. And why do we think that that would be the case? We know from purely a computer science perspective that an abacus and a conventional computer, your laptop, even a supercomputer, these are in some senses equivalent. They can efficiently simulate each other, whereas a quantum computer is fundamentally different. It operates according to fundamentally different rules, and we would like to leverage that difference in real life. We would like to exercise that discrepancy. So we develop a goal to reach a well-defined computer science milestone, which we say we achieve when a quantum computer performs a task that may be a contrived task, but a task that would take too long or would be too resource intensive for any classical computing machine. Okay, so what task might that be? Well, the ideal task should be solvable with quantum hardware. Okay, of course, we need the quantum computer to be able to achieve this task. It should be very difficult to solve on any classical hardware so that we can really observe the quantum classical distinction in practice. And it should be easy to check using classical hardware. That will allow us to make sure that the quantum hardware has been doing its job correctly. So some ideas that might come to mind, especially if you've had an introductory course in quantum information, might be factoring. We know that there's Shor's algorithm. You are saying the rightmost bit of the screen is cut off. Can you not read what's there?
Sorry, we can read everything. I just wanted to let you know privately that there's a very tiny strip, so we missed the last.
Okay. If it starts to become unclear, please let me know.
Please continue. It's just if you could move a window or something so it disappears, it would be easier for the audience.
Let's see. Did that help?
No, it's still the same. But it's okay. I think we can infer what's written there. It's just the last letter or two that's missing. Okay.
If this becomes unclear, let me know, and we'll try to work around it. So if you are familiar with Shor's algorithm, you might think that factoring would be a nice task for this, or even function inversion. We know that function inversion is a quantum computing capable task. Unfortunately, the quantum hardware that we're able to build today is not yet sophisticated to run algorithms of this sort, or to run these particular algorithms. So we have to go back to the drawing board and come up with a different task for demonstrating beyond classical performance. Well, if we have to give up one of these three bullet points on our wish list, we certainly can't afford to give up the first one. The second one is also critical. So we can drop the third and consider what an alternative task might be. And the task that we've chosen instead is, in some ways, it seems like quite an obvious thing to do on a quantum computer because it is exactly what a quantum computer excels at. We identify a particular quantum circuit, so a set of quantum gates, a quantum program, and we ask, what is the expected output distribution? In other words, if you were to run these set of gates on qubits and measure the output, you'll measure a 0 or a 1 for each qubit, you'll collect some set of bit strings, and you may ask, which bit strings are the most likely ones to be measured? Now, why would we pick that problem? Well, actually, it turns out that this is a well-studied problem, and it's been well-studied even within the classical computer science community. It is known that if we choose gates from certain distributions, and in particular, if we choose these gates, we choose how to fill in these white boxes. If we choose the identity of those gates from a random distribution, then that guarantees we will have that this particular problem of sampling, of determining which bit strings are most likely to be measured, has high computational complexity. So you can expect that if we are randomly choosing these circuits, we'll be exploring a very broad Hilbert space, and exploring such a large space will make it very difficult to determine, to follow or to emulate classically, to emulate that work on a classical computer. So, okay, we've identified that task. Now, how do we observe that, in fact, we can realize some beyond classical performance? Well, the steps would be like this. First, we would pick a particular circuit whose output distribution we would like to sample. And then we can evaluate what's the best quantum strategy and what's the best classical strategy. If you have a quantum computer, the best strategy is to simply run that circuit on your quantum hardware. If you have just a classical computer, it turns out that the best strategy for determining the output distribution is to simulate quantum mechanics. So you have to simulate the entire quantum mechanics running through that entire circuit. You could use a data center or a supercomputer. At the end, you can determine the classical cost that the quantum machine has labored. And then if we determine that that cost was too high, we say we've achieved our goal. Now, the tricky thing, or the kind of annoying thing about this is, in this case where the classical cost of reproducing the quantum machine's labor is too high, we actually cannot verify that the quantum machine did the correct thing, because the only way we can verify the quantum hardware's performance is by copying it on a classical computer. So in order to be sure that the quantum computer is operating correctly, we do some verification steps. And there are a couple of different ways we can verify. One is to model the errors that we can observe in bringing up our system in the first place, and build an error model, compare that error model to the data that we measure. And a second approach is we actually run two different flavors of quantum circuits. We have these so-called full circuits, which are very difficult to simulate classically. And then we have some other simpler circuits, which are just about as difficult to run for the quantum computer, but they have been sort of reorganized so that it's much easier for the classical computer to simulate them. And we can compare the performance of those two sets of circuits. So I'll go into a bit more detail on these. First, on the modeling. So we actually we build a model that is about the simplest model you could think of. It's based on the individual single qubit errors, the individual 2-qubit errors, and the measurement error that we have for each of these qubits, each calibrated individually. And then we can plot what this model predicts as we increase the number of qubits. So the fidelity on the y-axis is the chance of being able to run that full circuit and not see any errors. And then on the x-axis, I have the number of qubits. And the model wiggles around a little bit because we're actually taking into account the specific error that was calibrated for each particular qubit and pair of qubits. So if we start with, say, that block of 12 qubits, it corresponds to this first point on the model, and we can expand and draw this black line as a model prediction for our entire set of qubits. Then we can actually run some data and attempt to verify that the quantum computer performs according to what the model predicted. So we pick a circuit, we measure, we run that circuit on our quantum processor, we measure the bit strings, and we feed the circuit and the bit strings into a classical verification computer. That spits out an accuracy score. And that's the same accuracy score that I mentioned before that we use to characterize our gates. It's 1 in the ideal error-free case, it's 0 in the fully decohered case, and you can see we've got some number between 1 and 0.1 on this y-axis of the chart over here. But moreover, what we see, we plot these, we do this both for full circuits, which are in the red circles, and we also do some reorganization of the gates to make these circuits simplified and a little bit easier to simulate classically, or much easier actually to simulate classically. And what we see, moreover, is that the black line from our model prediction and the data that we have in the red and green markers overlap extremely well. And so this tells us that the quantum processor is working as we expect, and moreover, there doesn't seem to be any large system-wide errors that would need to be added to this model in order for it to describe the performance of the full system. That already is quite promising. We also observe, though, that you can see there's a little spot where we don't have that many red dots anymore, and that's because even getting up to 55 or 54, 53 qubits, this particular circuit has a depth of 14 layers. At that point already, this becomes very difficult to verify. We find that if we were to use a machine with 1 million cores, it would take 5 hours to just build that red dot. So we're already starting to feel a bit strained in our ability to truly confirm that the quantum computer is doing the correct thing. But okay, our goal was to push beyond the classical regime, so let's run some really hard circuits. We'll use 53 qubits and push into much larger numbers of cycles. We pushed out to 20 cycles, 20 layers worth of qubit operations in our circuit. And in this place, there are no red dots anymore because we cannot actually verify the full circuit, but instead we can reorganize the gates slightly and use those simplified circuits to confirm that indeed the performance of the quantum computer running those slightly simplified circuits does align very well with our model prediction. And moreover, we have a fidelity that is above 0. So this work, of course, relies heavily on the classical machines that we use to confirm the performance of the quantum computer. And that work has been done in close collaboration with a number of different supercomputers and other classical computing experts in simulating quantum mechanics. There are basically 2 strategies that are used for that simulation. One we call the Schrödinger simulation, and the method for this is to store all of the amplitudes and simulate the full circuits. So this is very memory intensive. If you wanted to do this for the largest circuits that we have simulated, you would need a computer with dozens of petabytes of memory. And if you had such a machine, you could do it, you could finish the simulation in a few days, probably. If you don't have a machine with dozens of petabytes of memory, I won't fault you. You're in good company, and instead we could take a hybrid approach we call the Schrödinger-Feynman simulation strategy, which involves basically using that same Schrödinger approach, but cutting the circuit in half periodically and simulating the individual halves, and then using a Feynman path integral inspired approach to stitch the paths back together. And in this case, we were working 1 amplitude at a time. So you're sacrificing space for time, in essence. And that works. Now you could cut down your memory requirement, say to something like terabytes. Unfortunately, the time scale is not too favorable, and in order to finish that, it would take something like thousands of years. So no matter how you split it, the take-home message is that to achieve the same processing on a classical computer would require ridiculous amount of resources. In the end, our processor, which we've called Sycamore, can run a 53 qubit circuit for out to a depth of about 20 cycles, and it can do that with non-zero fidelity. So that sounds a little bit weak, but in fact, the claim is, or the observation is, sometimes the quantum computer has no error. And we can well distinguish that case from the case where it is fully decohered. What is, to me, perhaps even more exciting is that the fidelity of the performance is in fact well predicted by a quite simple model that just comes from the individual single and 2 qubit gate errors and the readout error. There's no larger scale terms that we need to use in order to correct or to understand the error that we're observing. So with that, we say we have demonstrated our small milestone computational task, and looking ahead, well, sort of both reflecting and looking ahead, what's happened here. There's some interesting takeaways from the computer science world. I hinted before that in computer science, we have some proofs that a quantum computer works fundamentally differently from the classical computer. And finally, for the first time, we can build a system where we can really kind of feel that in action. In the future, we would like to add additional qubits and observe that difficulty scaling. It becomes, as I kind of hinted before, with every additional qubit, twice as difficult to simulate classically. But we already experienced this on this plot here. As our circuits got larger, we really hit a wall quite quickly of what we could simulate. And then finally, from a physics perspective, and really from a systems engineering perspective, this is an observation that quantum mechanics still works at highly complex systems, and we can build a highly complex quantum system that we can still control. This is relevant in part because there have been real questions in the community as to whether it's possible to control such a large Hilbert space, whether it's possible to build such a large system of individual quantum objects and control them all. And at least to the 53 qubit level, we were able to build this fully programmable system and still control it. So this gives us some motivation to think that quantum computing is in fact possible. And yes, it will be very difficult to build additional, to scale this further, but at a fundamental level, our understanding of the errors and the modeling of those errors is favorable and is promising. So with that, I would like to say thank you and acknowledge my teammates, and also thank you for your attention. And I think we're at time, so I will take some questions.
Thank you very much, Dr. Giustina. That was a fantastic talk. I really enjoyed it, and I think many people in the audience did as well. If you enjoyed it in Zoom, please go ahead and start the clapping. So use your little clap icon if you can, if you know how to use that. Or if you enjoyed it in YouTube, please feel free to write some expression of your appreciation in the chat. And of course, if you have questions, now please enter your questions, raise your hand in Zoom. And on YouTube, please enter your question in the chat. And I saw that there were already some on YouTube that I will get to very quickly. So I think what we will do first is get to the YouTube questions. Is everyone able to see me in the top right corner of the picture here? I think there might have been someone who's unmuted. Let me see what we've got in YouTube. So are you still there, Marissa? I think I lost your picture on.
Oh, I'm still here.
Okay, great. So the first question from YouTube is, how long did it take to build the prototype with how many people working on it simultaneously?
That's a good question, and not so easy to answer. We have been, so the building process required a lot of different pieces of technology development. I've had a different set of slides that I will sometimes use to show each of those. The pieces of technology that we needed to actually build in order to get from the 9-qubit system to this system that I'm showing here spans not only this integration of the chip itself, but also the package. We had to completely change the package, so we had to develop a brand new package system from scratch. we needed to change the way we were running signals. So we've used coaxial cables in the past, and we continued to use coaxial cables, but we increased probably in the first year. I joined the lab in 2016. Between 2016 and middle of 2017, we probably increased the number of cables in the lab by over an order of magnitude. And between then and now, it's probably been another order of magnitude. So we learned things like, now you can accidentally plug in your cables in wrong because there are so many of them that you can make mistakes that you couldn't make before. We also had to change the way that we did some of our filtering and amplifying. So there were a lot of pieces of development. And then on top of the whole thing, there was the software stack, which in itself took probably an additional several months to bring up once the physical chips were in place. We've also built a couple of different prototype chips. We had another chip that we announced at some point called Bristlecone. That was an earlier device that we built and started cutting our teeth on the calibration process and learning some things that work better than others. We've been pursuing a couple of different qubit architectures in our lab for a while, and so kind of working in parallel on all of those. It's difficult to say how many people specifically were working on which thing. Instead, I would say that we had this team during the time that this work was being done. The team was growing from around, I'd say, 50 people to the 70, 75 that we have now, and all of those people were working in some capacity on getting this system to work. It's given that it was a research task, it's not as simple as, well, you do step 1 and then step 2 and then step 3. It was really a set of distributed efforts across the lab, the learnings from which all fed together into getting this one system to work well. So
okay, thanks
maybe
a lot.
that
we've got a bunch of questions, so I think that was a great answer.
Okay, I'll try to keep it snappy. Sorry.
Some more. Next question will be from Zoom. Benjamin Levitan, would you please unmute yourself and ask your question?
All right, so thanks for that really, really nice talk. I had a few questions, but I guess I'll just pick one. So when you showed us,
feel free to show your video, Ben, if you feel like it's okay.
It's okay. I can find. Here we go.
If not, it's okay too.
Why not? So when you showed us these colorized images of the Sycamore chip with your error rates on it, it seemed like a few of the couplers were especially bad, and I was just wondering if there's anything to say about that. Like, what's wrong with those bright ones?
I mean, especially bad compared to
the others.
I think that's maybe an artifact of what you get on a heat map. I wouldn't say that they're really bad per se. I think it's more that yellow is the difference between this color and this color is more obvious than the difference between this color and that color. In general, the single qubit gate calibrations are better than the 2 qubit gate calibrations because there's the single qubit errors can add to the performance of the 2 qubit gate. So when you're trying to perform a 2 qubit gate, if either of your qubits decoheres, you are sensitive to that. So it's harder to get a good 2 qubit gate than it is to get a good single qubit gate. So if you look at this, you can kind of see that the single qubit errors are from around here to around the middle, and then the 2 qubit are from around the middle to the top. But to me, it actually looks like a pretty even distribution.
Right. Yeah, I can see the argument. Can I ask a second question on the same slide?
Mm-hmm.
So it seems like readout is substantially harder than the gates from the error rates.
It is.
What's the principal limitation there?
Readout is hard in general. So what we're trying to do in readout land is determine for a particular qubit whether or not it contains a single photon at around 5 gigahertz. 1 photon at 5 gigahertz is not very much energy. That's like the ambient temperature would be about 300 millikelvin if you're talking about, if you want to grasp it physically somehow. So the way we do that is actually involves some pretty significant microwave gymnastics. And we have that additional resonator that I showed on the slide with the image of the micrograph. We actually couple that resonator to our qubit very weakly and then probe that resonator, whose frequency will shift depending on whether or not the qubit has a photon floating around in it or not. But this is sort of indirect and requires a lot of time and a lot of extra physical materials. We need this additional resonator. We need amplification because, okay, now we're still only getting about 15 photons worth of information out of that second resonator. That needs to be amplified up to something that we can probe at room temperature. Whereas a gate, you just have to send the information in. You have to hit the qubit, but you don't have to get anything out of the qubit. Amplifying a single photon level signal is much harder than attenuating a heavy signal and shaping a heavy signal from room temperature. So gates are hard, gates are critical, gates are really important. Readout is a whole different animal.
So
Okay,
is the challenge there in going from the qubit to the resonator, or it sounds like from the resonator to something you can actually...
If you could stick around for the après colloque, you could ask Dr. Giustina a little bit more in detail what's going on, but I think we've got a bunch of people waiting to ask questions. Okay, sorry to interrupt, but thanks for the question, and thanks for the answers, Dr. Giustina. So there's one from YouTube. Question from YouTube is, maybe from an aspiring quantum engineer, what skill sets are required for a quantum engineer at Google?
That is a good question. One thing that I would always try to impress on when I talk with students in physics and engineering is learn how to program well. More and more we are automating our experiments, and things that used to be done by hand, turning knobs, are increasingly done by writing a piece of software and letting the software do it for you.
Okay, thanks. So
I'm trying to be quick because you've said there are a lot of questions.
Great. It's because we've got many people very interested, and we've only got 5 minutes or so for questions, but definitely it'd be good if we can get through a couple more. So one more from Zoom. Kartiak Agarwal, could you please lower your hand and ask your question?
My hand is, yeah, okay. Yeah, hi. So thanks for the very nice talk. I had a very quick question. So when you said the Shor's algorithm can't be implemented, or just any general algorithm, is it because the fidelity of individual gates is kind of low, or is it because somehow you don't have a universal gate set?
It is not because we don't have a universal gate set, it's because the fidelities are too low.
Okay, I see. And you know, how much do you have to improve these sort of numbers that you've written down to be able to say do some kind of implementation of Shor's algorithm on these qubits?
So it is as much that the fidelities are too low as it is that the coherence times are too short. Shor's algorithm would require us to implement a long set of gates, and we will need to have an error-corrected system in order to actually physically implement that algorithm. So it's the time as much as anything.
I see. Okay, that makes sense. All right, thank you.
Okay, great. It seems we have another question from within Zoom. So Eamon Egan, can you ask your question? Unmute yourself and ask your question. Turn on your video if you want. Eamon Egan?
Yeah, hi. Can you hear me?
Yes, I can.
Yeah, I think that the previous fellow just more or less asked the question. I mean, I was just going to comment that you've basically, the benchmark test you set up is basically asking the computer a question about itself. And that's the level I'm at right now. I don't understand too much more than that. So I think you pretty much answered the question. You need more fidelity before you can tackle what I would call a real world relevant problem, unless you think this is real world relevant, but sort of things that people would, like traveling salesmen or factoring or whatever. We
believe that we will need error correction for this, that we will need an arbitrarily long-lived qubit. So the tricky bit here is that our fidelities are as low as they are. Our fidelities are limited by the coherence time of the qubit. You can set the qubit in a state, but it doesn't live there for very long. It loses the quantum information pretty quickly. What we gain from error correction is longevity. Error correction will allow us to set a qubit in a state, and it will live there arbitrarily long. And having that long-lived qubit state allows us to do much more exotic and elaborate algorithms than we can do with this very short lifetime that we have right now.
Do things just have to sit longer for more complex things to happen, or do you have to actually do things to it while the qubits are being, does it just need to sit there and bake for longer? And that's why it has to, if it's more complex, or is there something that has to happen to it that you're doing to it and the things have to live during that? I don't know if the question's clear. Anyway, that's my last question.
Let me try to answer it, and you can tell me if I've hit it. Imagine that you were trying to program a regular computer, like your laptop, but it had this strange feature that within 5 minutes of starting the computer, it would just fall apart. It would crumble. It would automatically shut down. Windows updates would take over. Whatever. You would be fundamentally limited in the work that you could do. You could only get done what you could do in 5 minutes.
Okay.
It's a similar thing here. We can do algorithms that run very, very quickly, but any algorithm that is longer and more complicated takes more steps. We can't do because the quantum computer has decohered. The quantum information has gotten lost before then. So that is a fundamental metric of quality needed in order to run some of these bigger, more interesting, more real-world applicable programs.
Okay, thank you.
Okay, we have one more question from YouTube, and I think it's going to be our last one because we're running out of time. We're right at the edge. So the last question from YouTube is one that I wondered about myself, but I think it was probably answered in your plot, but I'm not sure. So the question is, does the difficulty of increasing the number of qubits scale polynomially? And scale polynomially is in quotation marks.
The difficulty of increasing the number of qubits, I think it scales non-linearly, and it is very dependent on what number you are at. So I think this means like arbitrarily into the future. So to get from 53 to 54 to 55 to actually build a couple more qubits should be about as difficult as it was to build the 53. However, at some point, we will have a limiting factor, like we're going to run out of cables in the cryostat at the spacing they have now. And so we will need an entirely different approach to installing cables or to wiring up a cryostat. Or at some point, we're going to run out of space on the chip, or we're going to run out of package space, and we'll need new technologies there as well. And just as the very first question was asking about what did we need to do in order to actually build this prototype, there were technology developments needed across the board. Similarly, we'll have those moving forward. So wiring is a big one, and packaging not unrelated, but also all of the amplification that's needed in readout actually runs pretty hot. So the most taxing energy dissipative part of our system is the amplification that we need to amplify those teeny tiny few photon signals up to something that we can read out at room temperature. And doing readout more efficiently will also become a limiting bottleneck pretty soon. So it'll probably be more like a step function of it's about the same amount of difficulty, and then you hit a wall and you need to develop a new technology, and then you can cruise on that for a little while until you hit the next wall.
Okay, thanks. So I know there are a lot of people who want to ask a lot more questions. I've seen more in the YouTube chat, and in fact, people are putting their questions in the Zoom chat just to try to squeeze them in. But unfortunately, we have a kind of time schedule. We're trying to make sure the après colloque can start at a sensible time. So let's thank Dr. Giustina again for a really, really good colloquium. I really enjoyed it myself, and I'm sure a lot of other people did. Please clap in Zoom or say something in the chat in YouTube. And now, so I'll just remind everyone to come back next week, Friday at 3:30 p.m. Eastern time for another edition of the Physical Society Colloquium. We'll have Philip Phillips from the University of Illinois at Urbana-Champaign to talk about condensed matter theory. He's going to talk about, or I think the title of his talk is Beyond BCS Theory. So it's going to be about superconductivity. It should be a very interesting talk. And with that, thanks everyone for joining. Please come next time. I'll see you